Good evening to all of you. Good evening, dear. I hope my voice is clear to all of you. I hope my voice is clear to all of you. Okay. So today we will be discussing a new topic, that is gradually varied flow. So today is lecture number 9 and we are going to discuss about gradually varied flow. So complete discussion about gradually varied flow I will be doing here. Gradually varied flow. Majorly in a gradually varied flow, we are dividing this big topic in a 3-part. First one, I will be giving you the differential equation, or sometimes we also call this as a dynamic equation, differential equation of GVF. So this is the first part of this topic. Next thing which I will be discussing is the length of the GVF profile. How to find out length of the GVF profile. So that I will be discussing. That is the second part. Now in this third part will be the classification of slopes. So that classification of slopes, and with that numerical related to that classification of slope, we will be discussing tomorrow. So GVF part 1, part 2 will be there. Today is the part 1, tomorrow will be the part 2. Okay, so let's start discussing with the GVF part first. Okay, I think GVF basic definition already I have given you, na? At the starting of my discussion, GVF I told you it is nothing but the when there is a small change in depth for a long span of time or long span of distance, we call it's nothing but a gradually varied flow. We call it's nothing but a gradually varied flow. Okay. 1 second here. Okay. So whenever there is small change in depth which is occurring in a long span of distance or time, we call it a GVF. Now what are the causes? First one is the change in the cross section. You know that when there will be a change in the cross section, the depth will increase, na? So first reason is nothing but the change in the cross section. Second is the change in friction. Change in friction means what? For example, this is a channel bottom. Here we have less friction and here we have more friction. Then what will happen? What will happen to the depth? You will find there is an increasement in the depth. Why it is increasement? Because if there is a more F, that means more friction, here the velocity will be less. So if velocity will be less, area of the cross section will be more. Here the velocity will be more, area of the cross section will be less. So you can see there is a change in the depth which is occurring because of the change in friction also. So here also the GVF is caused. Next one is the obstruction of the flow. So obstruction of the flow, it is like you have seen the example of dam. This is your channel cross section. This is your channel bottom. This is your channel bottom. This is the dam. This is the dam. Now if you know that water is coming from this side, that is the upper stream side of the dam, what will happen with the water? Slowly it will started changing its depth. That means it is rising so that it can cross the dam part. So this part, you will find there is a change in the depth. There is a change in the depth for a long span of distance. We call it a gradually varied flow. Now change in slope. Change in slope, if you see, for example, there is a mild slope which is going on. After that we have a horizontal slope. So this is a mild slope. This is the horizontal slope. Okay. If you are not getting what is mild, what is horizontal, I think at least this you can understand. Now here the slope is 0, S is 0. So this is the horizontal slope. And this line, this surface is having some particular slope. Definitely it is more than the horizontal. The slope value is more than the horizontal. Now what will happen with the water? Here the water movement will be fast. But as it is coming to this horizontal zone, it will started increasing its depth. Why it is increasing its depth? Because here the velocity will be less. So to compensate that lower velocity, it has to increase the velocity. It has to increase its velocity. So in that case, the depth will rise. In that case, the depth will rise. So there is again change in depth for a particular length of time, or you can say for a long length of time. So in that case, it is nothing but the example of GVF. So these are the causes how a GVF can occur in your day-to-day life or in a real life, you can say, not day-to-day life, real life, how a GVF can occur. So these are the causes which you need to understand it. These are the causes which you need to understand it. Now, as you understand that GVF is nothing but it's a non-uniform flow. Na? It is not a uniform flow. It is a non-uniform flow. So for non-uniform flow, to proceed further, we need some assumptions. So what are the assumptions we have? First one, as always, we take flow is steady. Second, pressure distribution is hydrostatic. That means we are taking all the streamlines are straight and parallel. Head loss is similar as that of uniform flow. So what they are telling that head losses are similar to the uniform flow. So slowly we are trying to make this non-uniform flow as a uniform so that we can proceed our analysis further. Okay. Next, channel slope is small. They are saying that channel slope will be there, but it will be very small. Kinetic energy correction factor alpha equal to 1. You know that alpha equal to 1 is for what? It is for uniform flow. So alpha equal to 1. Channel roughness is constant. So even channel roughness also they have given as a constant only. So if you see all the assumptions, they actually tries to make this non-uniform flow as a uniform flow. So that calculation, so that the analysis will be easy. Na? That is the purpose. Now look at my dear. I have given a note for you. Generally, when we write Manning's equation for uniform flow, na, in place of slope, we use bed slope. There is a very, I will say very important difference which you all guys have to know. When you write Manning's formula for uniform flow, here this S is longitudinal slope, S naught, bed slope. Clear? But when you write this formula for non-uniform flow, here it is a GVF. So in that case, V equal to 1 by N, R to power 2 by 3, R will be same only, but this time this S will be SF. That means it is energy line slope, not the bed slope. There is a very small and very important difference which you need to understand, that when you are using Manning's equation in a non-uniform flow, that S will be the SF. Clear? Kindly note it down. Kindly note down these things. Is it noted? Okay. So now I will be deriving a small derivation for you. Small derivation. There is nothing but the dynamic or differential equation of GVF. Easy definition is there. No need to worry about. So this is the channel datum, or you can say datum line. This is the channel bottom, or this is the water surface line. You call this as HGL also. Then this is the red line. That means it is nothing but the energy line. Okay. So for this line, the slope will be S0. This line, the slope will be SW. This line, the slope will be SF. So this depth we call it as nothing but Z, elevation head. This we call nothing but Y, depth of the flow. And this is nothing but the velocity head, V square upon 2G. If you want, you can write down this part. This is the total energy line. This is the HGL line. I think till here, nobody is having any doubt. Here few things are unknown to you, or you can say already some like S0, SW at least already known to you. S0 is what? Channel bottom slope. Channel bottom slope with respect to horizontal. SW is what? Water surface slope with respect to horizontal. dy dx is the water surface slope with respect to the channel bottom. That is the difference between dy upon dx and SW. SW is also water surface slope only, but that is with respect to horizontal. dy dx is nothing but also water surface slope only, but it is with respect to the channel bottom itself. Okay. Now, if you look at my dear, total head I can write like this now. H is equal to y plus z plus v squared upon 2g. I don't think so anybody will have any problem. Y plus z plus v squared upon 2g. Now, what I'm telling you here, let us differentiate with respect to x. So, this will be dh upon dx, dy upon dx, dz upon dx. You can take 1 upon 2g as common. So, this will become, okay, this we are getting. Copy it fast. Copy quickly. Okay. Now look at my dear. This is the total head. It is going in the downward direction. So can I write like this? dH upon dx. dH upon dx. Can I write like this? Minus SF as it is going in the downward direction. Similarly, I can write dz upon dx also as minus S naught. Why I am writing this? Because you can see this water surface line as well as the energy slope line or energy line is going in the downward direction. So in that case, I can say it's a minus slope, negative slope. Okay. Now put this part here in this equation. Now we are having minus SF equal to minus S naught plus dy upon dx plus 1 upon 2g d upon dx v square, that is q square upon a square. Okay, equal to 0. Sorry, equal to 0 is not there. So you can put S naught in this side. So it is S naught minus SF equal to, we are having dy upon dx. Now this will be q squared upon 2g. I am keeping outside. This will be d upon dx. I can change this little bit now. Like I can write this as d upon dy. Bracket we have 1 upon a square into dy upon dx. I don't think so anybody will have any problem in this. So S naught minus SF dy upon dx plus q squared upon 2g dy upon dx into. Now if you differentiate 1 upon a square with respect to y, it will be nothing but minus 2 1 upon a cube dA upon dy. Is it clear to all of you? I hope you got this point. Now dA upon dy, what we can write this part? dA upon dy. While explaining critical flow analysis, I have given you this part. In place of dA upon dy, what we can write? You guys can comment. So dy upon dx I am taking as common. 1 minus this 2 and 2 will get cancelled out. 2 and 2 will get cancelled out. So you will be having q squared upon g. Okay. This is nothing but dA upon dy we can write as t. So t upon a cube. This we are getting. So I can write dy upon dx is equal to S naught minus SF divided by 1 minus q squared upon g. Q square t upon g into a cube. G into a cube. So dy upon dx is equal to S naught minus SF 1 minus c. This you can change it also. Like q squared upon a squared, you can write this as v square. A by t you can write as g into d. V square upon gd is nothing but what? V square upon gd is nothing but what? It is proud number square. So fr square. So you got a formula for dy upon dx is nothing but equal to S naught minus SF divided by 1 minus fr square. Here we have assumed that our channel bottom is also going in the downward direction. This we have assumed. This you need to take care. For this formula, we have assumed our channel bottom is going in the downward direction. If you want, you can write down so that you will not forget this. Note you can write channel bottom is falling in the direction of flow. In the direction of channel bottom is falling in the direction of flow. This you need to assume it. And this we have already assumed it. So this equation you need to always take care that this equation channel bottom is falling in the direction of flow. It's a very important equation. This equation we call as dynamic equation or differential equation of GVF. This equation we call as dynamic or differential equation of GVF. Note down quickly, note down quickly. We'll solve one problem based on this. Chaliye. So here's the problem. You all can try. Okay. Now look at all the given data first. It's a 2 meter wide. So B is 2 meter. Then bed level is rising in the direction of flow. It is 1 in 10,000. Okay. So here they are telling bed level is rising in the direction of flow at a slope of 1 in 10,000. That means it is rising. That means S naught you need to take as 1 upon 10,000 with a negative sign. I hope you got it. Why we have taken? Because in a formula which we have derived, we have assumed our channel bottom is falling in the direction of flow. Here it is rising just opposite. So we need to take minus sign for that. Then Q is given to you. Very good. Manning's coefficient is given to you. N is given to you. The flow in this reach is gradually varying at a certain section in the reach, the depth of the flow. So Y is also given to you. The rate of change of water depth with respect to the distance, dy upon dx at this section is. G is taken as 10 meter per second square. Okay. So let us solve this problem. See, we need to find out dy upon dx. So formula is S naught minus SF divided by 1 minus FR square. So for Froude number, first of all, V upon root under G into D. It is a rectangular section, if I'm not wrong. So D will be equal to Y. So it is V upon root under G into Y. So let us calculate V first. We have discharge, that is 4, na? Divide by 2 is the width and 0.5 is the depth. So 2 into 0.5. So this is 10. So basically 4 we are getting. So let us calculate this. 4 divided by root under G, we have 10.5. So basically it is 4 divided by under root 5. How much we are getting for that? 1.788. This is the F Froude number value which we are getting. Now second thing which is unknown to us is SF. For that, what we will do here? We can use the formula V equal to 1 by N R to power 2 by 3. It will be SF now. It's a non-uniform flow. So SF to the power 1 by 2. V we can write 4 meter. 1 by N. Slope is given to you 0. N is given to you 0.01. R. It's A by P. It is not a wide rectangular channel. Na? It is a normal rectangular channel. So area by perimeter will use it. So area will be 2 into 0.5 divided by 2 plus 2 into 0.5 to the power 2 by 3. SF we need to calculate it. SF we need to calculate it. So 4 equal to 0.01. This is nothing but the 1. 2 into 0.5 is nothing but the 1. Divide by 2 plus 0.1 to the power 2 by 3. In bracket we have SF to the power 1 by 2. SF to the power 1 by 2. So can you calculate SF for me? Can you calculate SF for me? So roughly what I'm getting around 6.92 into 10 to power minus 3. So S naught we are having minus 1 upon 10 to power 4 minus SF will be 6.92 into 10 to power minus 3 divided by 1 minus FR square, so 1.788 whole square dy upon dx. How much we are getting? Roughly what I'm getting around 3.19 into 10 to power minus 3. I hope you guys have noted down. Okay. Now the next thing is the length of the water surface profile. Now let us start our derivation from the beginning. H equal to what we are having? Z plus Y plus V squared upon 2G. Now, this Y plus V squared upon 2G I can write in this way. Z plus specific energy. Now again differentiate with respect to X. So dH upon dx, dz upon dx plus dE upon dx. Now dH upon dx I can write as SF minus SF. This is minus S naught dE upon dx. This I can write as S naught minus SF is equal to dE upon dx. S naught minus SF is equal to dE upon dx. I can write this in a different way. Dx is equal to dE upon S naught minus SF. So this is nothing but the formula to find out length of GVA profile. Delta E, this you can write in this way also. Delta X is equal to delta E S naught minus SF. You can write in this way also. Now for this, to find out the exact value of delta X, now we have two different methods. First method we call it single step or direct step method. In that actually what we are doing now, for example, let us say this is the channel bottom. Understand it. This is the channel bottom. This is the dam. Water is coming like this. If you take this section, you will have this y1 and y2. If I'm interested to find out this delta x part or this length part, so how we can calculate this part based on this method? See, formula is delta x is equal to delta E upon S naught minus SF. S naught will be given to you. Delta E you can find out. Difference at like E1, E2 difference you can find out. Now SF is like at Y1, at Y equal to Y1 you will have a different SF1. At Y equal to Y2 you will have different SF2. Like that means your slope is different, energy slope is different at different depth. Definitely it will be different. It's a non-uniform flow. So what we are doing here, we are taking average of this. So it will be SF1 plus SF2 divided by 2. That is something SF we are using in this formula, and then we are calculating this delta x. So basically we are calculating this L part. So this is the method that we call a single step or direct step method. Why we are calling it a direct step method, Vishad? Because here you have taken only 2 points. At y1 you have taken the SF value, y2 you have taken the SF2 value. But what about the complete water surface profile? You have not considered the complete water surface profile. It means you are giving your value based on only 2 points. In between whatever the points is coming, you are not considering in your analysis, which is not good for us. So this method will give you a approximate data. It will not give you accurate data. And you will find I will also explain you. This is the reason why we are not using this for a non-prismatic channel. This method we are not using for the non-prismatic channel. We are only using for the prismatic channel. This method is not suitable for the non-prismatic channel. Okay. Now this is the right method. But now in numericals or in exam problem and all, what we have find out a shortcut for that. Like I see 2 times you will be finding SF1, SF2. That means 2 times you will be using Manning's equation. Calculation will be lengthy and all. So in numericals, what we are doing, we are taking y1 and y2, and as an average, we are finding ym. And that ym is nothing but equal to y1 plus y2 divided by 2. Now for that ym, we are finding a SF value. So only one time Manning's equation will be used. And that SF value we are using in this formula to find out delta x. So that is not the right way, but as a shortcut technique, we can use it. So this is the first method that we call as single step or direct step method. Kindly note down quickly. So as I am giving you demerits of this model is, it is less accurate and water surface slopes are not properly taken into account, which I have already given you. It is suitable for prismatic channel only, not suitable for non-prismatic channel, unlined or natural canal. So note it down, these things. These are the demerits of this model. In tomorrow's class, I will be discussing classification of slopes. With that, I will be solving few numericals also related to that. And that is very important discussion actually. By the way, each and every lecture is important, but that classification of slope part na, it is, I know it is very difficult topic for most of the student, so I will try to make it easy for all of you. Okay, so I hope you have copied this. Now the next technique is the numerical or graphical integration technique. Now what we are doing it here, if we need to find out L, we are just integrating this delta x. So basically it is delta E upon S naught minus SF. We are integrating it. When you integrate anything na, whenever you integrate anything, that means you are taking from y1 to y2 the complete water surface profile. The complete water surface profile you have taken into account. Definitely this method will be giving you more accurate data because you have taken the complete water surface profile. So I have given as a merit to you. Merit is it is more accurate compared to the direct step method, as by mathematical procedure of integration the surface profile is properly taken into account. Okay, now as it is a more accurate method, you can use it for prismatic as well as non-prismatic both type of channels. So that also I have written to you. So this we call as numerical or graphical integration method. I hope it is clear to all of you. This you can write in this way also, is equal to dE upon S naught minus SF. Kindly note it down. Till here we have completed two part of GVF. One part that is related to classification of slopes and all, that I will be discussing tomorrow. That is a separate part. For that we need a separate class. As I said, only 3 classes are needed now. So most probably Thursday, today is Monday na, so Tuesday, Wednesday, Thursday your syllabus will be over. Thursday your syllabus will be over from my side. Easy question, all of you can answer. Direct step method of computation for gradually varied flow is, it's a direct step method, so it will be only applicable to prismatic channel. Only applicable to prismatic channel. Direct step method of computation for gradually varied flow is only applicable to prismatic channel. Is only applicable to prismatic channel. Okay. So for today's class, up to this only we'll discuss. Tomorrow your GVF profile will be completed. That means the next topic, that will be a classification of slope. So tomorrow your gradually varied flow part 2 will be there. Till then, Take care. Good night. All of you will meet again tomorrow at 8 p.m. sharply.